All right, let's jump right into this explainer. For years, the systems programming world has been totally dominated by one big mandate: rewrite it in Rust. And, while Rust's massive success is absolutely well-deserved, there's actually a really fascinating shift happening right beneath the surface. We're stepping into what you could call a post-Rust renaissance, and it's being driven by three incredibly innovative languages: Zig, Mojo, and Carbon.
So, to really get this shift, we need to look at the core philosophy. That rewrite everything for safety approach, it's fantastic for greenfield projects. But let's be real, it can be an absolute nightmare for massive, decades-old legacy codebases. What we're seeing now is the rise of something else entirely: incremental interoperability. Instead of tearing down the old infrastructure and starting from scratch, these new languages are designed to natively integrate with it. They basically give you all those shiny modern features without forcing you to abandon your existing ecosystem.
Here's our agenda for today's explainer. We're going to cover the post-Rust renaissance, then we'll look at Zig's live binary editing, dive into how Mojo brings AI to systems programming, see how Carbon is modernizing legacy C++, and finally, wrap up with the systems programming convergence.
Let's kick things off with Section 1, Zig and live binary editing.
Now, in traditional systems programming, changing a few lines of C++ meant you hit compile and went to grab a coffee, right? Well, Zig fundamentally changes that whole architecture to hit a pretty staggering number: sub 300 millisecond rebuilds. Think about that for a second. It's essentially acting like a hot reload systems language. If you're prototyping a GPU driver or a high-frequency server, you change a function and boom, the binary is ready to run almost instantly.
So how exactly does it pull this off? It does it by splitting the build system right in two. In version 0.17, Zig introduced this dual-core architecture. First, you have the configurer, which acts like the brain. It analyzes the internal dependency tracker, they call it the intern pool, down to the exact source hash to find precisely what changed. Then, the maker steps in as the executor. Because the configurer already did the heavy lifting, the maker only does the absolute bare minimum work required. This means your build times scale to the size of your code change, not the size of your entire project.
But the real magic here is how the linker handles what Zig calls atoms. Instead of generating traditional object files on a disk somewhere, Zig maintains this live data structure right in memory, called the Zig object. Inside this object are atoms. Think of them as the smallest patchable chunks of machine code, like a single function. Crucially, these atoms contain localized relocation entries. This means the compiler doesn't have to go and recompute some massive global table every single time you make a tiny tweak.
This setup essentially turns Zig into a live binary editor. When you change a function, the compiler calls an update hook. It locates that specific atom in memory, swaps out the bytes, and recalculates only its local offsets. It then marks that specific section as dirty. When it's time for the final flush step, it only writes those dirty sections to disk. Your external C objects and unchanged libraries, they are left completely untouched. And that, right there, is exactly how you get a 300 millisecond rebuild on a massive project.
Moving on to Section 2, Mojo, where AI meets systems.
For the longest time, AI researchers lived comfortably in Python, but actually getting hardware acceleration meant you needed deep C++ or CUDA knowledge. Well, Mojo bridges this gap by making MLIR, that's multi-level intermediate representation, a first-class citizen. Now, usually, MLIR is this highly complex tool hitting deep inside a compiler, but Mojo just exposes it. It basically turns the compiler into a programmable pipeline, where developers can write custom passes directly inside the language, optimizing high-level Python-like code way before it ever touches the actual hardware.
This pipeline is an absolute game changer. Let's trace it out. Mojo represents the code in MLIR, it lowers that down into LLVM, and then finally it lowers it all the way down to your specific target hardware, whether that's NVVM for NVIDIA, ROCm for AMD, or Metal for Apple Silicon. This allows AI folks to write incredibly high-performance GPU kernels without ever having to learn CUDA, C++, or Rust. It gives you GPU portability right out of the box, which is just a massive leap forward for heavy workloads like LLM inference and diffusion models.
And to keep everything safe, Mojo uses a very specific ownership model. Now, while it is heavily inspired by Rust's strict rules around memory safety, Mojo's model is uniquely engineered to manage really complex tensor lifetimes and GPU buffers. Because it integrates directly with that MLIR pipeline we were just talking about, it can guarantee memory safety across all those different hardware targets, and it does it without ever relying on the unpredictable overhead of a garbage collector. It's giving you the safety of a hardcore systems language, but with the ease of an AI scripting language.
So we all know memory safety is absolutely crucial these days. But let's pose a question. What do you do if you have a billion-line C++ code base that's been the backbone of your enterprise for the last 20 years? You can't just stop everything for 5 years and rewrite it.
That brings us perfectly to Section 3, Carbon, and the challenge of modernizing legacy C++.
To solve this massive enterprise dilemma, Carbon operates under what I think is a pretty brilliant philosophy. It aims to be the TypeScript for C++. Just think about how TypeScript revolutionized web development. You didn't just throw away all your JavaScript, right? You incrementally adopted TypeScript for the safety and clarity while keeping your existing runtime entirely intact. Carbon is doing exactly that, but for massive C++ investments. You get to incrementally adopt modern safety features, and you don't have to sacrifice an ounce of performance from your existing infrastructure.
So how does it actually pull that off under the hood? Well, most languages talk to C++ through a foreign function interface, or FFI, which almost always introduces data marshalling overhead in these really clunky wrappers. Carbon bypasses all of that nonsense entirely with a zero overhead bidirectional ABI. That means calling a Carbon function from C++, or vice versa, is literally as fast as a native call. There's zero translation penalty, none.
By aligning directly with the upcoming C++ 26 standards and using value semantics by default, Carbon ensures it can seamlessly coexist right inside your current infrastructure. It also offers a refined generics model that is way cleaner than C++ templates, but, and this is key, it remains totally compatible with them. So instead of holding a gun to your head and forcing a total rewrite, Carbon acts as a modernization layer that actually respects the decades of engineering investment you've already made.
Which leads us to Section 4, the Systems Programming Convergence.
When we take a step back and synthesize all of this, a really clear pattern emerges across the entire industry. Look at this breakdown. Zig pairs perfectly with C for game engines and embedded systems. Mojo pairs natively with Python to accelerate AI and GPU kernels. And Carbon integrates seamlessly with C++ for giant enterprise software. Interoperability isn't just an afterthought anymore. It's genuinely being treated as a core performance metric.
What you should really take away from all this is that we are in the middle of a massive paradigm shift. First off, AI workloads are definitively becoming low-level systems workloads. They require the kind of fine-grained hardware control that we used to reserve just for operating systems. Second, the lines are completely blurring between build systems, compilers, and runtimes, whether we're talking about Zig's dependency tracking configurer or Mojo's MLIR compiler passes. And finally, incremental interoperability is proving to be a much more practical, scalable solution for the industry than the old philosophy of just rewriting everything from scratch.
So I'm going to leave you with this provocative thought. As tools like Zig, Mojo, and Carbon prove they can integrate perfectly into our legacy systems, fixing our biggest problems without actually breaking our runtimes, we have to wonder what this means for the future. Are we witnessing the end of standalone monolithic systems languages? Because right now, it certainly seems like the future belongs to languages that know how to play well with others. Thanks for joining me for this explainer, and I'll catch you on the next one.